Hi class, we are taking a look at section 7.3 today, and before we do, try this warm-up. So if you haven't already done so, what you're being asked to do here is something that we did earlier in the year when we were reviewing some of our matrix theory. And you'll remember that we conceive of a square matrix as a linear transformation. In this case, a linear transformation from R3 to R3. That is, it takes in three-dimensional vectors like those here, x, those two vectors that are there, x and another x, and it'll take those in as input and then output other three-dimensional vectors that are, I don't know, some other place in three-dimensional space, right? There's going to be some geometric transformation that occurs in 3 dimensions as a result of applying this matrix through multiplication. If you have a 3 by 3 matrix, just recall that when you multiply a 3 by 3 matrix by a 3 by 1 matrix, that is these column vectors here, these are matrices, I guess, right? Very simple matrices that can be considered just vectors. So go ahead, if you haven't already done so, do the multiplication. Remember, it's row by column. Each time we do one of these multiplications, it feels kind of, well, it really is a dot product. So you're going to have this row times this entry, times this entry, times this entry, like a dot product, right? And then this row times this column, and then this row times this column, and each time you're going to be taking it, again, a dot product, you're going to be getting one number for each of those, and those will be your 3 numbers that you are like loading into your vector. Hopefully this is all coming back to you. So if you haven't already done so, but now you're remembering how to do it, go ahead and pause the video, give it a try. In a second here, I'm going to reveal both solutions. Okay. So here you go. Did you get these 2 things? Hopefully you did. And so what are you supposed to notice here? Well, if you haven't already done that reflection yet, then go ahead and pause the video and do that as well. But hopefully you're noticing there's something kind of interesting about both of these results, actually. The first one, you'll notice that it seems very similar. The result we get seems very similar to the matrix we started with. It looks like it's just taking the vector that we started with, -5, -4, 3, and it looks like all it's doing is kind of scaling it up by a factor of 10. It's like multiplying, like as if someone could say, hey, instead of multiplying by that entire 3 by 3 matrix, I just want to multiply by the single number 10 as like a scalar multiple, and multiply by the vector, and I'll just get the same thing you got. And that person would be right. Huh. Interesting. Now, feel free, I should have given you a third vector as well. Feel free to try it on another vector. This vector just happens to be kind of special. In general, this matrix takes vectors and takes them all over the place. This matrix takes vectors all over the place. The second one also is kind of a little bit strange, but I guess you can think of this as a multiple as well. 0 times this vector gives you this vector. So maybe there's something there as well. This is just something to kind of, as a little teaser, to foreshadow what we're going to be doing in our lessons today. The community builder, if you haven't already thought about the community builder, is also a foreshadowing of our lesson today. It's very interesting, this idea of a matrix that really just has a scaling action on a vector, and what is so special about this vector. We're going to learn today about eigenvalues and eigenvectors. We're going to do really only the first part of section 7.3, but in order to really get into 7.3, we need to know enough linear algebra to know about eigenvalues and eigenvectors, but I can get you there. There's some more foreshadowing on this slide, as usual. You know how I like to kind of give away the lesson with a little picture at the beginning. Take a look at that Mona Lisa, and you see anything interesting? In particular, let's look at the blue vector. What happens to the blue vector under that shear transformation, that like kind of tilting transformation? And the answer is, looks like nothing. Interesting. So again, we're starting to see something happening here. There's like vectors that when transformation is applied, don't do nothing. Nothing happens to that vector, or at the very least, just some scaling in that same direction. Okay. Now today, I'll just say this as a little bit of a disclaimer. We're in the middle of a differential equations course, but there's not going to be a single differential equation today. It's all going to be a focus on the linear algebra piece. So recall that we say that vectors are linearly independent. Let's index them 1 through k. We've got k vectors. We're using subscripts here, or excuse me, superscripts to keep track of them. We mean that they're linearly dependent if there's some set of constants that when you multiply them by them, that is, and add them, that is a linear combination, like you see here, you get 0. And just to be clear, this is the 0 vector. That is, you get the vector 0, 0, 0, 0, etc. Okay, so what does that mean? I mean, that's maybe, I think a lot of you already understood kind of what linear dependence meant, and I think maybe we framed it in this way before, but the other way that maybe you're more comfortable with is to say that like one vector can kind of be written in terms of the others. So just verify that that is what this basically says as well. It's just said it in a slightly different way. Another really key word in this phrase here, in this definition, is this word right here, non-zero. Because obviously it's trivial. It's always true that you can put zeros in there for C1, for C2, etc., all the way up to CK. If you put zeros in there, of course you're going to get the 0 vector on the right side. So we're looking for a combination of C1s through CKs that give you 0, that are non-zero, that are trivial, that are not trivial constants, right? Is kind of the idea. So if it's true that that only works if the C1 through CK are 0, then it's linearly independent. That is, there is no, every vector is independent of the others. They can't be written in terms of each other. So we've said that a couple ways throughout this course, but I just thought I'd emphasize that again here. It's going to be a really important part of what we're talking about today. So let's take a look at this set of vectors. If I gave you only 2-dimensional vectors, it would be pretty easy, just upon inspection, to see that they are either linearly independent or dependent. When it comes to 3x3 vectors, it's a little harder to just look at them and know whether they're linearly independent or dependent. So that's why I wanted to do this one, because it's a little bit trickier to work through. And we're going to be able to bring up a lot of important ideas in linear algebra by just looking at this one example. So let's talk through it. I encourage you to pause the video and just think about what it would take to show this, how you would show it. Could you come up with those constants? It's a little bit tricky. Okay. Well, I trust that you've done just a little bit of reflection on that, and I'll give you some other opportunities to stop and do some reflection as I move through this example. But like it just says above, I guess what we're trying to find are C1, C2, and C3 such that you get that linear combination that you see in front of you ending up 0. So what is it that we're looking at there? What is that kind of object? We've got C1, that's a constant, like a scalar, times x1, which is this column vector, etc. So what does this end up being? What kind of mathematical object are we working with here? And the answer is, it's a system of equations, right? This is a system of equations with 3 unknown variables, C1, C2, and C3, and with 3 equations, right? Just to be really clear, this is the system we're talking about, isn't it? Think about what we just said. It's C1 times 1, 2, negative 1, plus C2 times 2, 1, 3, etc. We can rewrite this in this augmented form instead. And now we'll use row operations to reduce this matrix. This is something we did at the beginning of the year, but we'll do it again right now. So here we go. I'm just realizing that there might be a row switch in my example, but whatever. For the point of this example, I think it's going to be okay. You'll understand what I mean. Okay, so here's what we do to reduce a matrix. Really what we're about to do is just glorified and very organized way of solving the system by elimination. That's really what we're doing. So to do that, notice what we're going to do here is we're going to try and eliminate some variables. We're going to do this in like a really systematic way. And so recall the thing that we want to do is kind of get zeros here and here. Because if we go back to like what that really means back in the original equation, this is like 2c1, and this is a negative 1c1, and and those, if we can get that to cancel out with the C1 in the original equation up at the top here, this first equation, then we'll have eliminated C1 from these two equations. And we'll have just like a system down here, we'll have like a system of two equations that have no C1 in them. And that would be good. That would be like a good place to aim for, because that'll be like a system of two equations and two unknowns, which is simpler. That's the kind of the big idea as we move through this, but there's obviously more here. But this is a systematic way of reducing a matrix that you could teach a computer. In fact, that's the thing that's implemented on your calculator. You can use it. It's called reduced row echelon form. So we're kind of going with this. But we'll see. We won't quite get all the way there. So my idea here is to get rid of this and this. So the way I'm going to do it is I'm going to take R1 and leave it exactly as it is. I'm not going to change it at all. Just write it back down. Just immediately copy it. For the second row, I'm going to take R1 and multiply it by -2. And then I'm going to add it to R2. Doesn't this kind of comport with what you would have done if you were doing like systems of by elimination? You would like multiply one equation by something so that it, when you add it to the other, a variable goes away. That's what we're doing here, right? So when you do that, verify that this is what you get in that second row. If you multiply this first row by -2 and add it to the second row, you end up canceling out the first terms, 0. That first constant is going to be 0. And then, for example, here we get -2 times 2 is -4, plus 1 is -3, so -3, and so on. And R1 plus R3 will just immediately cancel out the first constant there. So just verify that also the last row, I replaced the last row with R1 plus R3. And now as we move to try to get ones here and here, that's the next goal here, is to get ones here. Notice that I can just divide through by -3 and -5 to, I mean, ideally what I want is like 1 and negative, I wanted just really a 1 here. I should have maybe left it as a 1. But either way, now you can easily see I can just add those together to get zeros in the last row. These, in fact, you might have even seen this kind of coming. You might have thought, oh, this is not that good. We've got two rows here that are basically the same. Now, typically, what we want to do is we want to keep going, and hopefully we get, eventually, if the solution is consistent and independent, that means that we'll have like a point solution, and the thing we'll get on the left side, if we can continue through this process, which we're not going to keep going with this, I'll show you why in a second, is we'll get the identity matrix here for this square matrix portion of the augmented matrix. And then that would be just like the solution of the system. C1, C2, and C3 would be equal to the three things you have on the right side. But here, let's interpret what we have, because something interesting has happened. Whenever we have this kind of situation where we get like a row of zeros after doing some reduction, it means there's some dependency. Okay, so I'm already kind of hinting at what the answer to the actual question is here. So let's write down again what that means in terms of the constants from the problem. There they are. Remember what this literally means: C1 plus 2C2 minus 4C3 equals 0, etc. So we get these two equations, and what my claim is that we've kind of got an undetermined or under-constrained system, right? We've got two equations and three unknowns. That means we should, like, one variable, one of these C variables must like depend on the others in some ways, right? We've got like a free variable in here. So just to make sure we're clear on this here, take a look at this. We're going to set C2 equal to 3C3, and we're going to let C3 be whatever we like, right? So C3 is whatever we like. C2 will let equal from the second equation, just rearranging it here. C2 will end up being 3 times that, and C1 will be dependent on whatever our two other variables are. So since it's a free, unconstrained choice, let's let C3 just arbitrarily be 1. If we do that, then we automatically get if C3 is 1, then C2 will be 3. And if C3 is 1 and C2 is 3, then take those into this equation right here, to find that C1 is negative 2. So then we have this relationship between the vectors that we've just found. And so that shows the actual dependency that we're looking for. So isn't that great? That's wonderful. That's what we wanted. And yeah, so that's good. And now before we go any further, some of you might have been thinking as we started this that as soon as you saw a system of equations, you thought, oh, I know a number of different ways to solve a system. Maybe you even thought about matrices. But I want you to think about this. Matrices, if you're thinking of an inverse matrix method, that will fail here because there isn't an inverse for a matrix like this, where the determinant isn't 0. And in fact, actually, you can do that as a check here as well. You don't actually have to find the dependency if it's not asked. Now here it is asked in this problem. It says if they are linearly dependent, find a linear relationship among them. So we did that. But if all we wanted to know is right out the gate, just like are they linearly independent or dependent, then we really could just check the determinant really quickly and see that, for example, for this set of vectors, we put them in a matrix like this, that we get something that isn't, that we get something that's 0. And if the determinant is 0, then bring back to mind things you know about matrices and linear transformations. If the determinant is 0, that means a few things, right? It means that remember, that's the scalar triple product that we talked about in multivariable calculus of 3 vectors. It's also the volume of the parallelepiped that's like defined by those 3 vectors in space. And also just think about linear transformations. If you have a 3x3 matrix that is a linear transformation, what it does is it takes vectors and transforms them. Imagine that this is actually the case for this one. Imagine that it takes vectors and pushes them all down to a plane in 3-dimensional space. If all your matrix did was like rotate space, then an inverse matrix would of course exist, because all you have to do is rotate space backwards, and you'd be like, yep, you moved all the vectors this way. Pardon me, I'm just gonna rotate them back. Everything's fine. But if the thing I did was to collapse them all to a plane, that is, imagine maybe just like kind of projection operation, right? So you've got like a plane in 3-dimensional space, and you've got all these vectors floating around 3-dimensional space, and I just want you to like create their shadows on that plane in 3-dimensional space. Notice that there's no way, if I've done that, there's no way for you to recover. There's no way for you to recover the original vectors once I've done that operation. And now also think about, for vectors of that kind, what will the volume of the parallelepiped be if they're in the plane together? If they're all coplanar, then that volume will be 0. So there you go. There's the determinant connection. The determinant of a linear transformation where we get this kind of collapse of dimension, this non-invertibility, is going to always be 0. So that's a long explanation and a good reminder, I hope, for things that you've already thought about. There's one other lens on this that I want to bring in as well, and that's from first semester in multivariable calculus. We thought about this idea of a system of equations before, and remember that when we were doing a system of 3 equations and 3 unknown variables, recall that geometrically that each of those is its own plane. So as we consider that, we've got 3 planes. Maybe we even want to, instead of C1, C2, and C3, let's recast those in the variables x, y, and z like we would have done in multivariable calculus. By the way, there's popcorn in the corner on this slide, just to remind you that you don't need to take notes on this. It's also a different color slide, just to kind of, this is a throwback. It's not needed. It's just extra. I think it's a connection you're going to enjoy. So remember, as we go to do that, the solution that we just got, we found this dependency. So with our variables, that's with x, y, and z, that's this. And I just want you to remember, like, what kind of geometric objects are possible if we're looking for the intersection between 3 planes. Certainly 3 planes can intersect with at a single point. That's kind of a desirable situation in a lot of cases, maybe. But what is happening here? Because clearly we didn't get a point. What else can be possible? There's also possible there's no intersection, right? And then, if you will recall, there's the possibility that 3 planes will intersect in a line. And there's also kind of a very trivial case where all 3 planes coincide. And I think you'd probably be able to see that right out the gate, probably, because they'd be scalar multiples of each other immediately, the planes. So, and in that case, if you were doing that kind of row reduction operation that we were just talking about a minute ago, you would get 2 rows of zeros as you go to simplify that, as you go to reduce it. So let's see if we can't see what this is. I think maybe you have a hunch on this. If you have a hunch that it's a line, then you are right. It is a line, but it's a little harder to see in this form. Let me see if I can put it in a form that you really recognize. Again, let's let z be our free variable. Z is free to be whatever you like. In fact, I think you're more comfortable perhaps calling it t. So let's do that for a second. And after some substitutions, we'll get this, right? Z is just t, because z is free to be whatever it likes. So z is our free variable. Y is just like the last slide, right? Y is going to be 3 times that. And x will depend on both of the others in that sense. So we can combine those. Give it a try. Work through the details and you'll see that I'm right. And clearly that is a line. So you see that we have this free variable. This is what kind of linear dependence looks like. We kind of have this sliding variable that is free to be whatever it likes. It's still constrained, but it's got freedom of movement, kind of, right? That's what dependence means. It's one variable depends on the others, or the other 2 variables depend on the one, whatever you want to say. But they depend on each other. Okay, it is in fact a line. Okay, so now we are finally ready to talk about eigenvectors and eigenvalues. So take a look at this dot transformation over here. This is a 2x2 linear transformation. That is, it's a transformation from R2 to R2. And you can see in the animation how it takes vectors in R2 and does stuff to them to get other vectors in R2. Every linear transformation is going to be some composition of dilations, reflections, rotations, and shears. Those 4 things, right? So yeah, like I said, a lot of times it's going to be some combination. It might be hard to tell what the kind of underlying geometric parts are to a transformation. But there's something interesting that you'll notice about this one in particular. This one in particular, notice that there's something interesting happening with those red points along those red lines. You'll notice that points along those red lines are not moving. Some of these points are going for a ride, right? Like a major ride. Like if you focus your eyes on one, like let's say up here, you can see that these points where we start here, let's watch it go. It's moving, 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 moving. And so this vector that goes out to that point is going from like here to here. Like it's going to move. That vector is going to move. But if you focus on points along either of the red lines, you'll notice that those vectors, even though the whole world around them is changing in drastic ways, vectors along this red line enjoy no movement at all, or if there's some movement, rather, it's just along the red line. It's just scaling out. Maybe it's just doing, it looks like along here you're getting a little bit of a scaling. As you go from here along here, it's just moving along that line. And same with the red line. It looks like it's kind of coming in along that red line. And these kind of these red lines, there's a sense in which, even if you don't know what everything else is happening in the picture, there's all sorts of movement happening. Those give you a little bit of a grounding. You're kind of thinking, okay, this is even if I can't describe it fully in terms of all those geometric transformations, I do have a sense that these characterize the transformation, that there's like movement in this direction, movement in this direction. Everything else kind of adapts to those 2 things. It's kind of fun. I'm not going to go through it right now, but this activity is quite fun if you want to link to it. I've obviously have the slides posted. And it gives you a chance to this activity to look at a vector field like the one here and make some guesses as to what you think the eigenvector will be, and see if you can't find those vectors that don't change under the transformation. It's a fun, intuitive way to get into this idea of eigenvectors and eigenvalues. So let's be precise though, and this gets back into what we were hinting at in the warm-up today. What we're looking for is certain vectors that multiplying by the matrix A for those vectors is just the same as if we had multiplied by a scalar, right? I hope that you understand that that's really kind of what we're getting at here. This picture is helpful. And so just to be precise here, what we're saying is we want, again, A times X, where A is a matrix, X is our column vector, let's say. We want that to be the same as the effect of just multiplying by some number. It's tradition, no matter who you are and no matter what linear algebra textbook you're using, to call that scale number, that scalar, lambda. I'm going to move those terms on the right side to the left. I don't think I've lost anyone yet, but just do keep track of what's going on here, because we're doing, some of you may not be real comfortable with moving around these kinds of vector symbols. Notice that, for example, when I moved it over, 0 on the right side appears, and that's not just a 0, that's the 0 vector, right? It's like a column of zeros. Make sure you're keeping score. A is a square matrix. X is a column vector. Lambda is a scalar, a single number, and X is a vector, and 0 is the column vector of zeros. Now this next move, make sure you're okay with that too. Again, something that's so simple when we're just doing algebra with normal numbers, it's just like factor out an X on the right side. First of all, it matters which side you factor something out when it comes to matrices, right? Like I can't factor X out to the front. It doesn't make sense to do that. This is a right multiplication. So it matters in linear algebra like which direction you're factoring, because multiplication is not commutative. So we're going to move that X out on the right side. Hopefully you get that. You'll also notice that an I slips in there. What does that stand for, Mr. Chase? I, capital I there, stands for the identity, the square matrix identity of the same, whatever dimension, the same as matrix A. So take a second to verify that that is, in fact, that does actually make sense here. In fact, it wouldn't make sense at all to have an A minus lambda in here. Just A minus lambda? What does that even mean to have a matrix minus a single number? No. That doesn't make sense. So just verify that this, take a second to kind of work through the details of this, that this really does mean the same thing as this last line. All right, now then just do some reflection on this. What do you have here? You have highlighted here, you have a matrix highlighted in yellow that takes, when you multiply it by our column vector X, takes us to the 0 vector. That would have to have determinant 0 if that were true. Now, if that's the case, then we have this requirement now in the box that the determinant of that quantity that we highlighted in yellow, that has to be 0. And that is enough to find our eigenvalues. So just to be clear, we just said that has to be true. And that lambda, that scalar number, is called the eigenvalue of our matrix A. And the unknown vector X, which points along those red lines in that picture, for example, those vectors that are just scaled by a matrix are called the eigenvectors. So, for example, notice in these, for this matrix that I have here, that the red vector 1, 1, 0 is an eigenvector. Why? Well, because notice that when I multiply by it, it has just a scaling effect. And then you ask, a scaling effect? By what? And the answer is -2. So now you've identified both an eigenvector and the eigenvalue, -2. So they come in kind of pairs, right? Notice that there might be, I keep saying eigenvectors and eigenvalues. Notice that there might be more eigenvectors and eigenvalues to find for a given matrix. But this is certainly one of them, isn't it? This pair is an eigenvector-eigenvalue pair for this 3x3 matrix. The word eigen, any German speakers out there? Eigen means self or characteristic, which makes sense. Like I said, these kind of red lines in the picture are special, right? These are the vectors that kind of characterize the entire transformation. So now the next question is, now that you know what they are, and if I gave you one, it would be very easy for you to show me that it works. But the next question, of course, you're dying to know is, how do you find them though? You're myself, right? It's easy for me to check, Mr. Chase. It's easy for me to check that you're right, that such a vector, an eigenvector and eigenvalue really are an eigenvector and an eigenvalue for a given matrix. It's easy to check. You just multiply and see that it does the same thing as scaling. But how do we find them? Let's turn now to that question. We use those two things that are in boxes on that last slide as the answer, right? So let's do it for just a 2x2 matrix, and this example will round out our lesson for today. So take a look at this. We said, if we're first searching for the eigenvalues. So we said that the thing that's going to get us those eigenvalues is imposing this condition that the determinant of A minus lambda I is we're going to force that to be 0, and that's going to give us those eigenvalues. So notice that what I have here is really in the end no longer really a matrix equation. Notice that this isn't a vector 0 anymore. That's the number 0. And this is a determinant here. These bars, we're taking a determinant here. So as we go to take that determinant, what do we get? Well, if we take the determinant, you remember how to do a 2x2 determinant? Just take the determinant along this diagonal, multiply, minus the product on this diagonal. Simplify, clean things up, and factor. We've given you one that factors nicely here. And so there we get two values that are possible for lambda. And you guys, this matrix has, you're going to come to kind of expect there to be two eigenvalues for a 2x2 matrix. Although there could be some interesting things that could happen with a quadratic. You think about it. What else could happen besides getting two distinct eigenvalues in this situation here? There's a couple other interesting situations that we're going to have to go through. But let's assume that it kind of comes out nice in this nice way. We get two real distinct eigenvalues. There they are, the eigenvalues, hooray. Now wait, we also need for each of those, the red and the green, we need an eigenvector. So now let's think about how we do that. Let's just look at the red one, the lambda 1, we're calling it, which is 2. So remember what we just did for lambda 2, I guess this was the case. We said for an eigenvalue, if you have a given an eigenvalue, then it should be true that its eigenvector, this should hold, right? We wrote that on a slide just a minute ago. Remember where this comes from. This comes from the fact that we required ax to be the same as lambda x, right? So all I've done here is just plugged in lambda equals 2 into that requirement. So what do we get? As we simplify those, notice already there's something interesting happening. And this is always going to happen. You're always going to get, if it's really an eigenvalue, then what you're going to get in the top row and the bottom row, if it's at least in a 2x2 situation, you're going to get this obvious dependence. But there's going to be some linear dependence happening. If it's a 3x3 matrix, you're going to get a linear dependence among the 3 rows. Anyway, so here we go. So what can we do? Well, honestly, we can take either row here. So if we take both of the rows give the exact same relationship between x1 and x2, right? So for example, the first row gives x1, do the multiplication, 1 times x1 minus, if we go row by column, minus plus negative 1 times x2, right? So it's x1 minus x2 equals the first entry here, 0. Notice if you did that with the second row, we're not even doing it, but if you were, you'd get 4x1 minus 4x2 equals 0. But of course, that's the same equation. And that is not a coincidence. That's the kind of thing that will always happen if you really did find an eigenvalue. So we get this x1 equals x2. So we can pick an eigenvector of whatever scale we like, right? You can, some people normalize them so that it's like, 1 over root 2, comma, 1 over root 2, right? That could be your vector. But the point is, any vector you like, you want to name here is fine for the eigenvector, provided that x1 is equal to x2. There's that linear dependence, right? So this is a pretty simple eigenvector. It's just the two components have to be equal. So notice that these always have to come in pairs. As you report your answer, you want to give the eigenvalue and the eigenvector pair. So 2 and 1, 1 are one of the pairs for this matrix. Now let's find the others. In green, we've got our second eigenvalue, and now I want you to just proceed to do that same process. Now, the first time I did this a second ago, you had never maybe done that before, so you letting me walk through it was appropriate. But I want you to try this one. Go ahead and pause this and see if you can't figure out the eigenvector that goes with this eigenvalue. So you're going to plug it in where lambda should go. Clean it up. Well, it's just obvious again that those rows this time we're not even trying to be it's not even sneaky at all. Those two rows obviously give the same information. So multiply either one of those by our vector and you'll get this equation, which gives us again a relationship between x1 and x2. So let x2, I'm solving here, let x1 be 1, let's say. We're free to pick whatever we like for one of them and then find the other, right? So whatever you like, just pick some convenient numbers, right? Pick 1 for x1 is, I think, a good choice. And now we have that other eigenvalue, eigenvector pair. To summarize, here are the two sets of eigenvalues and eigenvectors in red and in green that we got for this matrix A. All right. So things are going to get a little more complicated, right? What happens in the situation where eigenvalues are not distinct and real? What happens when we're doing 3x3 matrices and things like that? So, but this is a really good first introduction to the idea, the intuition, the theory behind eigenvalues and eigenvectors. And I hope you're finding this kind of fascinating. If you do, I think you're going to enjoy the rest of our study. But then I also commend you I encourage you to take a linear algebra course in its fullness. I don't know if I've dropped that hint enough this year, but obviously you're going to need to take more linear algebra because you love this, don't you? You do. Oh, sorry, one more comment. Could you check your work on this? Sure. Remember what it means to be an eigenvalue or an eigenvector? Go back to the original matrix and multiply the original matrix by this vector and see what happens. I think you'll be delighted. Take the original vector, the original matrix, and multiply by this vector and see what happens. I think you'll be delighted. And then one final comment as we go to look at our last slide here. One final comment, and that is, how does this all relate to systems of differential equations? Again, we didn't ever mention differential equations at all today. So there's more to the story here. You'll see that the bulk of the kind of heavy lifting in the theory when it comes to systems of linear of differential equations, the heavy lifting is going to be done by the machinery that we just talked about today. So the differential equations part will not be that hard if you know this theory today. We're just going to kind of drop the theory right in. It's going to all just come right out beautifully. So that's my promise to you, but we'll pick it up next time as we finish 7.3 in our next lesson.